Bismillahirrahmanirrahim. In the previous two lectures, I have explained the colligative properties in detail, and the first one colligative property was the lowering of the vapor pressure. So in this lecture, I will explain the second colligative property, which is the boiling point elevation or boiling point elevation of the solutions. And briefly, colligative properties are those which depend on the amount of the dissolved solute, but not on its chemical identity. That means these are the mass dependent and the mass dependent of the solute in the solution. So these are the learning objectives. At the end, you will learn why the boiling point of the solution is higher than that of the pure solvent, and I will explain with the thermodynamic parameters the reason about the boiling point elevation. And the second one objective is the benefit. What are the benefit of the boiling point elevation? That means we can determine the molecular mass of the solute. And there is a brief derivation. Actually, you will learn how to derive the equation that will be used to calculate the molecular mass of the solute. And at the end, I will discuss some of the very brief exercise on the calculation of the boiling point elevation, which is the delta TB, and the molality of the solution. And these are the two most important calculation out of the benefit of the colligative properties, which is over here is the boiling point elevation. So coming to the point, actually, if you plot a pressure, this is the vapor pressure and here's the temperature. So there are the two colligative properties which I will explain through this graph. One is the elevation of the boiling point, and the other one is the freezing point depression, or you can say the lowering of the freezing point of the solution. So if you just look at the graph over here, this is the x-axis, this is the y-axis. So the temperature is increasing from here to this side. So if you just have a look at the vapor pressure of the solvent, and this is the vapor pressure of the solution. And in the previous lecture, we have explained in detail the vapor pressure of this solution is low as compared to the vapor pressure of the pure solvent. That's why this line is above and this line is below, because this is having low vapor pressure as compared to the pure solvent. So if you just have a look over here, this is the boiling point of the solvent, and this is the boiling point of the solution. That means boiling point of the solvent is low as compared to the boiling point of the solution. That's why this is called the elevation of the boiling point. And the difference in the temperature between the solution and the solvent, actually, this is the boiling point elevation. So if you can see over here, this is the freezing point of the solvent and this is the freezing point of the solution. Solution is having low temperature as compared to the pure solvent. That's why this is called the freezing point depression as compared to the solvent. And the difference between these two temperatures, this is called the freezing point depression. And you can easily calculate with the sum of the equation. And in the next graph, I will explain in detail individually about the boiling point elevation and the freezing point depression. So the first, as in this lecture, I will discuss only the boiling point elevation. And now in this slide, I will explain the reason behind this one, why the thermodynamic parameters help us to give the reason about the elevation of the boiling point. And you know, there are the three main thermodynamics parameter. One is the change in free energy, one is the change in enthalpy, and one is the change in entropy. And here we are considering the change, change in free energy of vaporization, and the enthalpy of the vaporization, and the entropy of the vaporization, because this is the boiling point. That means solution is boiled or the solvent is boiled. So this is the state changing from the liquid to the vapor. That's why these are called the vaporization. All these thermodynamics are the change in vaporization of the free energy, enthalpy, and the entropy. So the first one is the so the first look at the change in entropy, and entropy of the solvent is least, and when you add a solute into the solvent, it forms a solution, and the randomness will increase. So the solution is having more entropy as compared to the pure solvent. And when these are evaporated, that means the vapor phase is always having more entropy as compared to the solution and the solvent, because this is at the gaseous phase. So if you just calculate the difference in entropy, that means the change in entropy from the liquid to the vapor phase in case of the solution and the solvent. So first, because the solvent is having least entropy and the solution is more and the vapor phase is more. So the difference between the solution to the vapor, that is called the change in entropy of the vaporization of the solution. And then a similar way, the change in entropy from the solvent to the vapor phase, that is called the change in entropy of vaporization of the pure solvent. So actually here we are computing the change in entropy of the solution with the solvent. So this is the change in entropy, and this is clearly visible over here. The change in entropy of the solution is less as compared to the change in entropy of the pure solvent, because the solvent randomness will be more from, because this is having least randomness. So when it is converted into the vapor phase, so the change in entropy will be more. So this is here the most important factor is the change in entropy, and conclusion is change in entropy of the solution is less as compared to the change in entropy of the pure solvent. So now the second important parameter is the change in free energy. And here the liquid and the vapor phase, this is the liquid phase and this is the vapor phase, are in equilibrium at the boiling point. So at the boiling point, the both phases are equilibrium, and that means the change in free energy or the free energy difference between the two phases are zero. So this is because when the system is at equilibrium, the change in free energy is the zero, and the boiling point will start when the both phases are at the equilibrium. So that means the change in free energy will be zero. And what about if this is zero? That means delta H will be equal to TB delta S, and here TB is the boiling point temperature. So this is just when you move over here, this will negative will become the positive, and this would be the final form of this one at equilibrium. So if you want to calculate the boiling point, so boiling point would be here. You just divide this one with the delta H, and this would be your final form. The relationship between the boiling point with the change in enthalpy or the change in entropy. So if the change in enthalpy is similar for the solvent and the solution. So this is, we are assuming that the change in enthalpy is same for the solvent and the solution. Then there is no change in the change in enthalpy. So what would be the relationship between the change in entropy and the TB? This is the boiling point of the solution or the solvent. In both cases you can discuss over here, but now look at the conclusion we have earlier made over here. The change in enthalpy of vaporization of the solution is less as compared to the pure solvent, and if this is less and this will be the more, then the boiling point will be more in case of the solution as compared to the pure solvent. And this is the thermodynamic reason why there is the boiling point elevation, because the change in entropy of the vaporization of the solution is less, so the boiling point would be more, and that is called the elevation of the boiling point. So this is the thermodynamic reason. Now I am going to discuss this is the final equation here. The boiling point, the change in boiling point, the boiling point elevation, that is called the delta TB. Kb is the molar boiling point elevation constant, and m is the molality or the molar concentration. And here it is clearly written, this is not the molar, this is the molar. And in detail, I will little bit explain in this lecture, but in a separate lecture, I will explain how to calculate this molar concentration. So now I am discussing actually how you can get this equation. And I will be using the same graph. Now in detail, I will explain first the elevation of the boiling point. Now the consider at point A, this is the point A, and you know this is the vapor pressure of the pure solvent, and this is line is the vapor pressure of the solution. Solution is having low vapor pressure as compared to the pure solvent. So this is the point A. So I am marking this point A. This is the boiling point of the pure solvent, because this is the line for the solvent. And if you draw over here, it cut at the x-axis, and this would be the boiling point of the pure solvent. At this point, it is evaporate, and what would be the this is of course this is the 1 atmosphere pressure, and this is called the vapor pressure of the pure solvent. This is called the P naught. So vapor pressure of the pure solvent, like in case of the water, it would be the 100 degree centigrade, and the pressure over here is the 1 atmosphere pressure. So this is the second point, and if you look at the same position over here, and this line cuts at the point C, and this point C, if you make it parallel to the x-axis, and it would cut at the y-axis. And this point, you know, this is the vapor pressure of the solution, and this is the vapor pressure of the solution. And actually, in the previous case, we have already discussed, if the temperature is same, at the same temperature, the vapor pressure of the pure solvent is more and the vapor pressure of the solution is less. And this is the lowering of the vapor pressure. Now, we have discussed the 2 points A and C. Now, if you extrapolate over here, that means if you want to boil the solution. This is the solution, this is the solvent. So I am now I am considering the point B. So if you want to boil the solution, so what would happen? What would be the temperature? You can just move over here to the x-axis, and this is the boiling point of the solution, because at this point the solution is boiled. That means if you want to boil the solution at the same 1 atmosphere temperature, then the solution will boil at high temperature as compared to the pure solvent. So this is the boiling temperature of the solvent, solution. And this is the TB naught I am considering over here. This is the boiling temperature of the pure solvent. So the difference between these two, that means this minus this, solution minus solvent, this is called the elevation of the boiling point. So this is very important, because I will use these 3 points to derive the equation. This was our final equation. So I will come to the end with this equation, with the points which I have discussed over here. So this is point A, B, and the C. I have explained in detail over here. So now, by taking the tangent at point A, that means now I want to get the slope of this one. The slope is the this one, change in y, and the change in x-axis. So change in y is this A to C, and change in x is A and B. So this is that means from A to C, this is the y-axis, and from A to B over here, this is the x-axis. So the change, the slope, let's suppose the slope is k, and this is dy over dx, changing of the values at the y-axis and the changing of value at the x-axis. So here dy is the AC and dx is the AB, as given over here. Dy is the AC and dx is the AB. Again, what is the AC? AC is the difference between the atmospheric pressure. A is the P naught and C is the P1. And in a similar way, over here, x-axis, A is the TB naught and B is the TBS. So just I have put the value over here. This is the difference. So I have put the difference over here, higher minus lower, and similarly higher minus lower. High vapor pressure minus low vapor pressure, and high vapor pressure boiling temperature of the solution minus boiling temperature of the pure solvent. And you know that this is the change in the vapor pressure, and that is called the delta P. This is the change in the temperature, that is called the delta TB, and this temperature is actually the boiling temperature. That's why I'm using the small b over here. This is not just the difference in temperature, but this is the difference, the temperature of the boiling point. So this is delta P, actually is the P naught minus P1, is the lowering of the vapor pressure, as in the previous lecture we have discussed in detail. And according to the Rawls law, this is equal to P naught x2. So P naught minus P1 equal to delta P, and this delta P is equal to P naught x2. Again, P naught is the vapor pressure of the pure solvent, and x2 is the mole fraction of the solute. And this is the Rawls law. So I am again, this k equal to this. This is the same equation I will be using from here. Now you can put the value of delta P equal to this, and over divided by the delta TB. So if you want to get the delta TB, that means the boiling point elevation, and this is the rearrangement, K will divide over here. And now I want to further simplify this equation. P naught over K, both are the constant. This is the vapor pressure of the pure solvent. This is a slope. This will remain a constant for a proper particle solvent. So let's say this is the proportionality constant, and I'm just labeling it. Let's suppose this is the Ke. So replacing P naught divided by K with the Ke, and this equation will become this equation. Now I am opening the equation with the mole fraction, and why I am going to do that, because our target is to calculate the molecular mass of the solute. So X2 is the mole fraction of the solute, and the mole fraction, mole fraction is the moles of the, if you want to calculate the mole fraction of the solute, so it would be moles of the solute divided by the total moles. And here total moles are the moles of the solvent plus moles of the solute. So in place of X2, you can put this one, because this is the general name, this is the mole fraction. So I'm just giving the detail of the mole fraction of the solute in this form. Now, if, because the concentration of solute is much less as compared to the pure solvent, then you can neglect the denominator over here. So this equation will become Ke N2 divided by N1. And now I am putting the detail of the moles. These are the N2 are moles of the solute, and moles of the mass, given mass divided by the molecular mass. So if N2, that means the mass of the solute divided by the molecular mass of the solute. And this is the N1, moles of the solvent. And if you open this one, this would be the mass of the solvent divided by molecular mass of the solvent. And if you just rearrange this one, this equation will become this. Now, this is the equation from the previous slide. Again, K is the constant as we have discussed before, and M1 is the molecular mass of the solvent. This is also a constant because the solvent will remain the same in the pure solvent and in the solution. And you know the molecular mass of the solvent, like in case of water, it is 18. So these two are again the constant. So I am just replacing the Ke M1 with the Kb, that is another constant. And this is called the molar boiling point elevation constant, or you can say this is the ebullioscopic constant. And this is the property of the solvent, and this is going to vary from solvent to the solvent. So I am going to replace Ke-M1 with the Kb as explained over here. Now this is actually your final equation, and this is the boiling point elevation. This is the ebullioscopic constant. This constant is known for a particular solvent. This is the W2 is the mass of the solute, and M2 is the molecular mass of the solute, and this is important. We can calculate by using this equation. And W1 is the mass of the solvent. So by using this equation, you can calculate the M2. M2 is the molecular mass of the solute. And now coming to the final equation in terms of the molality, and molality is the number of moles of the solute per kilogram of the solvent. Like in molarity, which is the capital M, we use the moles of the solute per liter of the solution. So don't miss up with the capital M. This is a small m, and this is called the molality, and the definition is given over here. So if you look at the this equation, and in this equation, this is the mass of the solvent, and this is the mass of the solvent in kilogram. So if you want to convert the mass in gram to the kilogram, you have to divide by the 1000. So I'm dividing the W1 with the 1000, not the whole equation. W1 divided by the 1000 to convert the mass of the solvent from gram to the kilogram. Now look at this formula. Actually, this is the molality. Why? Because M2 divided by W2 divided by M2, this is the given mass divided by molecular mass, and given mass divided by molecular mass are the moles, and here 2 is defining the solute. So these are the moles of the solute, and W1 divided by 1000, this is the kilogram of the solvent. That means you can replace this one with the small m, because actually this is the molality. And this is the final equation actually we used at the start of the lecture, and we have actually arrived the final form of the equation. Now, what are the units of the Kb? Kb is the molar boiling point elevation constant, and if there is simple to calculate the unit, just this would be the delta Tb divided by m. And this change in the boiling point, elevation in boiling point, simply this is the change in the temperature, and temperature you can calculate in Kelvin. And the molality is the moles per kilogram. So this is divided from over delta TB, and this will become kilogram per mole. And or you can even use the centigrade, the unit for the temperature, centigrade kilogram per mole, or the Kelvin kilogram per mole. These are the unit for the kb. Now the final exercise on the calculation of the molality. So the data is given over here. What is the molality of an aqueous glucose solution if the boiling point of the solution at 1 atmosphere is 101.27 degrees centigrade. So the molar boiling point elevation constant for the water is given over here. This is the 0.51 centigrade kilogram per mole. So what is your strategy? You have to use this equation, and you want to get the molality. Molality would be delta TB over KB. And here first you, because KB is given, you just have to calculate the delta TB, and delta TB is the, this is the boiling point of the solution is given, and you know you have dissolved this glucose in the water, and the boiling point of the water at 1 atmosphere is the 100 centigrade. So you just get the difference. Delta TB is the difference in temperature, or you call it the elevation in boiling point, solution minus pure solvent. So you would get the value of 1.27 degree Celsius, and just put the values over here, and the final answer is 2.5 molar. So the molality of the solution is 2.5. So this is very important. That means you can calculate the concentration of the solution if delta TB, or the boiling point of the solution is given. So with this one, this is all about this lecture.